Okay, welcome everyone. In this video, I want to talk about some properties that linear transformations may or may not have. And these properties hopefully sound familiar to you since these terms you probably have come across in a calculus course. So I want to start with something which is not a linear map. So let's consider the function f, which maps from the real numbers into the real numbers, where we take each number x and we map it to x squared. And we have a geometric interpretation of that map, right? As we can think about it as the graph of a parabola. And you probably recall from calculus that this map we would consider as not being one-to-one because it does not pass the horizontal line test. And that test is significant because that tells us, for example, here are two values, say -1 and +1, and they both have the same image. F of 1 equals f of -1 equals 1, right? So here we have two x values that are getting mapped to the same y value, so we say that that map is not one-to-one. We have the same terminology for linear transformation. So if we go up to higher dimensions, so now t is mapping from Rn over into Rm, and we know that t is a linear transformation. This map is said to be one-to-one, which you also may have referred to as being injective. So we say this map is one-to-one if each vector in the codomain, each b in Rm, has at most one vector in the domain Rm, which is mapped to it. So it's impossible for something in Rm, in this case, to have two different vectors in the domain that get mapped to the same image in the codomain. And that's the equivalent of thinking about the horizontal line test that you may recall from calculus. A second property of linear transformations I want to talk about is onto, which you may have also called a surjective property. So we say that a transformation T is onto if each b in the codomain has at least one pre-image x in the domain which is mapped to it. So in other words, the codomain and the range of the function are equal to each other. So every vector in Rm gets mapped onto by something in the domain. And so if we use this function f, which maps x to x squared, it happens to not be linear, but if we think about this mapping, it would not be an onto mapping because there's a whole bunch of y values down here, basically anything negative, which is not in the range of this function, right? So this function has a codomain of all of R, however, its range is just non-negative numbers. So really what we're interested in thinking about is the range equal to the codomain? Are we mapping onto everything in the codomain? And so that property we call onto. So these properties, one-to-one and onto, we can think about these properties really for any mapping, but they certainly also apply to particularly linear transformations. So let's take a look at some examples that we saw previously and think about whether those maps would satisfy these properties. So recall the dilation transformation T, which if we dilate by a factor of 1/2 has the following matrix. Well, that dilation transformation is both one-to-one and onto. And we'll talk about how we can verify that. And it's going to come down to looking at properties of the matrix representation of that transformation. So here, this is what's really nice about matrices and linear transformations. Any linear transformation we can write as a matrix, and then we can look at properties of that matrix and how they correspond to properties of the linear transformation. But a dilation transformation is both one-to-one and onto. The last transformation that we took a look at in the previous video was the projection. And remember, that smushed the elephant. And in that case, that map is neither one-to-one nor onto, since the image of this map is going to wind up with the second entries are all going to be 0. So in this case, every point in R2 is actually getting mapped to a point on the x1 axis. So we're not mapping to all of R2, so that's why it's not onto. And we also saw that there were multiple vectors that were getting mapped to the 0 vector, for example. So this transformation is neither one-to-one nor onto. And notice, hey, we've got a column that doesn't have a pivot over here, and maybe this is going to play a role in determining some of these properties.